Hello, my name is Avinav Goswami. This is the second part of the topic that we started in the last video, that is electric charges and fields. This topic is a part of the chapter 1 of class 12 physics textbook. And the topics that we are going to cover today are the basic properties of electric charges, Coulomb's law, forces between multiple charges, that would be the superposition principle, then electric field, then electric field lines. Let's start with the basic property of electric charges. As we all know that there are two types of charges, positive charge and a negative charge, and this positive and a negative charge always try to neutralize each other. Now there is one more important point. Let's say there are any two charges. Now if those two charges are far apart from each other, if the distance between that two charges is very big, then we can consider that the distance, as the distance increases, we can consider the charges as point charges. By point charge, I mean that we assume that there is no dimension of that charge, it is just a point in the space. Now let's talk about the basic properties of electric charges. The properties of electric charges include additivity of charges, then charge is conserved, and quantization of charges. Now first, let us talk about additivity of charges. Let us consider a system with two charges, Q1 and Q2. Okay, a system with only two charges. Then the total charge of that system would be given as Q1 plus Q2. That is the sum of both the charges. Now this theory can be expanded and we can consider a system with n charges, say Q1, Q2 up to Qn. Okay, let us consider a system with n charges up to Qn. Then the total charge would be given as Q1 plus Q2 plus Q3 up to Qn. All the charges would be summed up to get the total charge of that whole system. Now let's move to the second basic property of electric charge. The second property of charges simply says that charge is conserved. Now let us consider a system. Let's say the system is a neutral one, and let us consider that the system contains two objects in it, a woolen cloth and a glass rod. Okay, now the wool and the glass both separately are neutral, as well as the whole system is a neutral system. Now if we rub the glass rod to that woolen cloth, then charges would be transferred from one another, and the glass rod would be positively charged and the wool would be negatively charged. Now we have two objects that are charged differently, but the whole system is neutral. So we can say that there is no creation of charge in it. Charge cannot be created. Charge can only be transferred from one place to another. So electrons are transferred from the glass to the wool. So the wool is a negatively charged object now, and the glass is a positively charged object. But the whole system is still neutral because the amount of charge transferred would be same. The system consists wool and glass. So even if the wool and the glass are both separately charged, that doesn't make any difference to the system as a whole. The system would be neutral. So we can say that charge is conserved. For a given system, if we observe a given system, then we can say that charge is conserved. Now let's come to the third basic property of electric charge. This is quantization of charge. What happens here? The whole system have a charge capital Q, but this capital Q can be divided into single amount of charges. Now let's consider that single amount of charge is E, and for this system there are n number of E's, and combining those n number of E's, this n number of E's, we get the total charge to be Q. Now here E is the charge of an electron, which is given by this value. This is 1.602192 into 10 to the power minus 19 coulomb. Now we cannot get any charge less than this. Now electron have this charge, and in a body we always get a integral multiple of charge of this amount. This amount is always fixed. We will never get half of E, or we will never get 3 by 2 of E. We will always get an integral multiple of E. So we say that charge is quantized. Charge always comes in a definite amount of E, this value. We will multiply some number to this value and we will get the charge of a complete system. Now 6 into 10 to the power 18 electrons all total combined to give us one coulomb of charge, and the SI unit of charge is coulomb. Now let's move towards Coulomb's law. Okay, let us consider there are 2-point charges Q1 and Q2. Let us denote these charges as Q1 and Q2. There are 2-point charges and they are separated by a distance r in vacuum. The magnitude of the force F between them is given by F equal to K into Q1 into Q2 by r square. This is a qualitative statement about the force between these 2-point charges. The point charges are Q1 and Q2. Okay, so Coulomb's law give us a statement that defines the force between that 2-point charges we are observing. Okay, where Q1 and Q2 are the point charges and r is the distance between them. Now here we can say that F is inversely proportional to r square. F is inversely proportional to r square. Now here K is a constant, and let us say that K is arbitrary for now. We are not defining K right now. So let us say K is arbitrary, and in SI unit K is given as 9 into 10 to the power 9. We are considering vacuum here, so we will take 9 into 10 to the power 9. Since it is a constant, it doesn't have any unit. Let us say that these 2-point charges are unit charges. We will take 1 unit of the charge in SI unit. So SI unit is coulomb, which is denoted by C. So let's say the value of Q1 is 1 coulomb and the value of Q2 is 1 coulomb, and it is separated by a distance r equal to 1 meter. Since meter is the SI unit of distance, so let us say that r equal to 1 meter. Now putting these values in this formula, we get the value of F as 9 into 10 to the power 9 Newton. Newton is the unit of force. So this defines what is coulomb. So 1 coulomb is the charge when placed at a distance of 1 meter from another 1 coulomb charge in vacuum, and it experiences an electrical force of repulsion of magnitude 9 into 10 to the power 9 Newton. This constant K is usually put as K equal to 1 by 4 pi epsilon naught. This quantity here is called epsilon naught. So the Coulomb's law becomes F equal to 1 by 4 pi epsilon naught into Q1 Q2 by r square. This is the mathematical expression we use. So epsilon naught is called permittivity of free space, and the value of epsilon naught in SI unit is epsilon naught equal to 8.854 into 10 to the power minus 12 coulomb square Newton inverse meter inverse square. Now since force is a vector quantity, we can write Coulomb's law in vector notation. For that, now let's see in the figure. Here is a charge Q1 and there is another point charge Q2. So if we have an origin O, from that origin the distance of the point charge Q1 is R1 and the distance of the point charge Q2 is R2. Now we shall denote force on Q1 due to Q2 as F12 and the force on Q2 due to Q1 as F21. Same goes for the notation of the radius vectors. So the distance of Q2 from Q1 would be given as R21, which would be R2 minus R1, and the distance of point charge Q1 from Q2 would be given as R12, which would be minus of R21. Now using Coulomb's law, we get force on charge Q2 due to charge Q1 would be given as F21, which will give us the expression this 1 by 4 pi epsilon naught Q1 Q2 by R21 square. This is a magnitude, and here R21 cap, this is the unit vector. This gives the direction. Now if we change R21 to R12 using this formula, using this expression, then we will get a minus sign over here, which gives us minus of F12, which is the force on charge Q1 due to charge Q2. So we get that the force on charge Q2 due to Q1 is opposite of the force experienced by Q1 due to Q2. Therefore we can say that electrostatic force obeys Newton's third law. Now what happens when there are multiple charges, not just two charges? So force between multiple charges we can define in this way. Let us consider three charges here, Q1, Q2 and Q3. Now we are here to calculate the force on Q1. Now here Q1 is not only experiencing force from Q2 but also experiencing force from Q3. So the force on Q1 due to Q2 is represented as force F12, and the force on Q1 due to Q3 is represented as force F13. So the expressions would be for F12 this one and for F13 this one. Now the total force on Q1, the total force on this charge Q1 would be given as F1 equal to the summation of F12 and F13. Now this would be a vector addition since force is a vector quantity. Now this not only stays limited for 3 charges, this can be expanded for n number of charges. Now if in a system we have n charges, now the force on the charge Q1 will be given by F1, and F1 would be given as the expression this, which is the vectorial summation of the force experienced from each and every other charges. Now the next topic is electric fields. Now let us consider 2 charges, say charge capital Q and small q. Now let us say capital Q is in the position O and small q is in the position P, and the distance of O and P is R. Now force between these 2 charges would be given by this expression using Coulomb's law. Now what happens when this point charge small q disappears from this place? What happens then? Now let us say that the point charge small q is removed from the point P. Now there arises a question, whenever we remove this charge q from this point P, there is nothing in the space, but what was applying this force? There is no explanation for that. So scientists came up with the idea of electric fields. So they said that for this charge q, also for this charge P, there is a field around the charges. That field covers the entire space. Now whenever one charge comes into the field of another charge, force is experienced by this charge due to this field around this charge. Now electric field produced by a charge capital Q is given by this expression, E equal to 1 by 4 pi epsilon naught capital Q by R square R cap, where R cap is the unit vector. Now this is the expression for the electric field of this charge Q at a distance smaller. Now for any charge, let's say Q, whenever it is positive, the electric fields are radially outwards, and whenever it is negative, the electric fields are radially inwards. Also another important point is that we defined capital Q and small q. This capital Q is known as source charge and the small q is known as test charge. Now we bring this test charge in the field of source charge to test the field of this capital Q. Now it is important for this capital Q to stay in its own place, but there is a difficulty. But for the charge capital Q to be a source charge, the charge capital Q should always remain in its position. So to remove that difficulty, we assume that the charge small q is negligible in terms of capital Q. Therefore we can give electric field E with this expression, when limit small q tends to 0, force F by Q. Now as we can calculate force due to a system of charges, we can also calculate electric field due to a system of charges. It is the same procedure. If we consider electric field due to one charge Q1, that would be E1, and another charge Q2, which would give us electric field E2, then the electric field of the whole system would be given as E1 plus U2 plus E3 up to En. Now since E is a vector quantity, this addition would be a vector addition. Now since E is a vector quantity that varies from one point to another in space, so it is determined from the position of the source charge. Now let's see what is the physical significance of electric field. Now let's see here, for any system of charge, the measurable quantity is always the force on the charge, and it is determined by Coulomb's law and the superposition principle. Superposition principle is the Coulomb's law on a system of charges. Now, why we need this electric field? What is the physical significance of electric field? Well, for electrostatics, the electric field is convenient but not really necessary. But the necessity of electric field comes only when we go beyond electrostatics and deal with time-dependent electromagnetic phenomena. Suppose we consider a force between two distant charges q1 and q2 in accelerated motion. Now the greatest speed with which a signal can go from one point to another is c. C is the speed of light. Thus the effect of any motion of q1 and q2 cannot arise instantly. That effect of the motion of charge q1 and q2 cannot arise instantaneously. Now there will come some delay between the effect and the cause. Here effect is the force on q2 and cause is the motion of q1. The force that q2 is experiencing due to the motion of q1. Now it is precisely here that the notion of electric field is natural and very useful. The field picture is this, that the accelerated motion of a charge q1 produces an electromagnetic wave which then propagates with the speed c and reaches q2 and causes the force on q2. The notion of the field elegantly accounts for the time delayed. Now, even though electric and magnetic fields can be detected only by the effects of forces on charge, they are regarded as physical entities, not merely mathematical constructions. They have an independent dynamics of their own, that is, they evolve according to the law of their own. They can also transport energy. Thus, a source of time-dependent electromagnetic field turned on briefly and switched off leaves behind propagating electromagnetic fields transporting energy. The concept of field was first introduced by Faraday and is now among the central concept of physics. Now, what are electric field lines? Now, since we said that electric field is a vector quantity, so the direction of that electric field should also be given by vectorial notation. Let us consider that these lines are giving us the electric fields. And as it goes away from the charge, the length of these lines are decreasing, which means that the strength of that electric field is decreasing. But we don't necessarily need to draw this type of lines, because let us check in this position. Here the density of the field lines are more. We find the field lines more close to them, but here we find the field lines little bit apart from them. Now electric field lines are the concept in which we see the electric fields. It is not necessarily how it is there, but we define for ourselves, for our own understanding, that this way, that in this way the electric field lines travels and it delivers the action it need to deliver. Now here are some examples of electric fields. Now for a positive charge q greater than 0, the electric field lines are outwards. They move outwards from the charge q. For a negative charge q less than 0, the electric field lines moves inwards. Now here are two positive charges. So since positive charges repels each other, in this area all the electric field lines are moving apart from the other electric field lines. Now here is an example of unlike charge q plus q and minus q. So since two unlike charges attract each other, so here the electric field lines are moving from the positive charge q outwards towards the negative charge minus q, and finally it goes inside the charge minus q inwards. So in this way we can explain why two unlike charges attracts each other. Now let us see some significance of electric field lines. Electric field lines start from positive charge and end at a negative charge. If there is a single charge, they may start or end at infinity. In a start-free region, the electric field lines can be taken to be continuous curves without any breaks. Two electric field lines can never cross each other. If they did so, the field at that point intersects and will not have a unique direction, which is absurd. Now electrostatic field lines do not form any closed loop. Now we will see this concept in the second chapter. Now in the next class, we will discuss the topic of electric flux. So if you like this video, please give a thumbs up and subscribe to my channel. Thank you.